The innovative machine learning approach presented in this paper addresses the real-time load shedding problem in power systems, focusing on equitable decisions. It starts by emphasizing the importance of timely and effective load shedding to maintain supply-demand balance and prevent cascading blackouts. The authors discuss how optimization-based methods can balance economical and equity considerations but are often too complex for real-time computation. They propose a machine learning algorithm to identify binding constraints, simplifying the optimization problem to enable millisecond-level computation. The approach is demonstrated on both a 3-bus toy example and a realistic RTS-GMLC system, showcasing its validity and efficiency in delivering equitable and real-time load shedding decisions. In the realm of power systems, the equitable load shedding problem has garnered significant attention. Researchers aim to develop a more equitable load shedding algorithm that optimizes the distribution of load shedding percentages across nodes in a transmission system. This system comprises n buses and lines, with the objective being to determine the optimal load shedding percentage C for each node I to promote equity. The problem is formulated as a quadratic program, QP, that seeks to minimize total generation costs and load shedding while adhering to operational limits and fairness constraints. These constraints include DC power flow, nodal power balance, and operational limits for phase angles, generation, line flow, and load shedding. Moreover, fairness constraints are incorporated to limit bias in load shedding decisions. The research explores a learning to optimize approach for this problem due to its potential for efficient online solutions during emergency operations. This novel methodology could revolutionize how power systems manage load shedding, leading to more equitable distribution and reduced costs. The research paper presents a groundbreaking study on the application of machine learning algorithms to predict weather patterns. It introduces a novel approach combining traditional statistical methods with neural networks to enhance accuracy. The study focuses on the development of a predictive model that can forecast weather conditions with higher precision than existing methods. The authors emphasize the importance of incorporating local climate data and historical weather patterns to improve the model's performance. The paper also discusses the challenges of training the model on limited datasets and proposes strategies for data augmentation to overcome this limitation. The binding status of inequality constraints is determined using dual solutions, which are directly related to the neural network's input-output relationship. Dual variables are used to determine the binding status, while the neural network's layers are interconnected to achieve this. The binary cross-entropy loss function is introduced as a key component, alongside risk measures like value at risk, VAR, and conditional value at risk, CVAR, for load shedding operations. CVAR is highlighted as a more coherent risk measure, particularly for skewed distributions. Numerical simulations using a 3-bus toy example and a 73-bus RTS-GMLC system are presented to verify optimal solutions and demonstrate the efficiency of the proposed method. In power systems, the load shedding problem is a critical issue, particularly in systems with multiple generators. To address this, researchers have formulated an optimization problem to minimize generation cost and load shedding cost, subject to constraints on generation and load shedding limits, power balance, and an equity constraint ensuring that load shedding at each bus does not exceed 50% of the total load shedding values. By eliminating non-binding constraints, the problem is reduced to an equivalent linear system, which is solved to obtain the optimal solutions for generation and load shedding. To demonstrate the effectiveness of this approach, the authors consider a more realistic RTS-GMLC system consisting of 73 buses and 120 transmission lines, covering an area of approximately 250 times 250 miles in the southwestern United States. Numerical simulations are performed using a quadratic generation cost function and a consistent parameter lambda equals 104. The load shedding upper limit is set to S max I equals 0.40 for each bus, and an orthogonality threshold E equals 0.5 is adopted for the equity constraint. The load shedding decisions for all buses under different delta values are presented in Fig. 4, showing that a smaller delta promotes more balanced and impartial decisions. The learning performance and online computation efficiency of the approach are validated by varying the load configurations and solving the optimization problem repeatedly to collect learning samples. Specifically, the load at buses 5 and 27 is incrementally increased to generate 2,500 inputs, and each is solved to obtain learning outputs. Analysis of the learning samples reveals that the proposed approach can effectively learn and predict the optimal load shedding decisions based on the given features and constraints. The paper presents a machine learning algorithm for real-time equitable load shedding in power distribution systems. It formulates the load shedding problem as an optimization problem, aiming to eliminate bias among different loads. By learning the binding constraints, the optimization problem is simplified to solving a set of linear equations. This approach enables efficient and accurate decision-making in real-time operations. The authors use a neural network with 3 hidden layers to predict the binding status of constraints, achieving a prediction accuracy of 99.46%. The computation time for solving the optimization problem and linear system is significantly reduced, making it suitable for real-time operations. The paper discusses future work, including the investigation of efficient learning algorithms for equitable decision-making in network distribution systems.